Welcome! In this session, we'll explore LeetCode problem number 1270, titled All People Report to the Given Manager. This is a fascinating problem that involves understanding hierarchical relationships within an organization. We'll break it down step by step and analyze the most efficient approaches to solve it. Let's dive in. Here, we are presented with the problem scenario. Imagine we have a table called employee that contains information about each employee in a company. This table has columns for the employee's unique ID, their name, the department they belong to, and the ID of their manager. Now, if an employee does not have a manager, their manager ID is set to null, which would usually be the case for the CEO of the company. The task is to write a SQL query that identifies all employees who report either directly or indirectly to a specific manager, given their manager ID. The results should be sorted in ascending order by the employee IDs. The output of the query will be a table with two columns, the ID of the employee and their corresponding name. These will represent all employees who are part of the hierarchy under the given manager. To clarify, direct reports are employees who have the given manager ID in the table. Indirect reports are employees who report to someone else, but eventually, through the chain of command, also fall under the same manager. The results should always be returned in ascending order based on the ID. Looking at an example, consider an input table where we have employees like John, Sarah, Bob, Alice, and Charlie, each with their respective departments and manager ID relationships. Suppose we are given manager ID equal to 1. In this case, we aim to find all employees who report to John, either directly or indirectly. Based on the input table, Sarah and Alice are direct reports of John because their manager ID is set to 1. However, Bob and Charlie also fall under John's hierarchy, as they report to Sarah, who directly reports to John. The output table, therefore, includes the IDs and names of Sarah, Bob, Alice, and Charlie, sorted in ascending order by ID. Now, consider another example where the manager ID is given as 2. This means we are looking for all employees who report to Sarah, either directly or indirectly. In this case, Bob and Charlie are direct reports of Sarah, as their manager ID is 2. There are no other employees further down the hierarchy reporting indirectly to Sarah. Hence, the output table consists of just Bob and Charlie, with their IDs and names listed in ascending order. To further clarify, Sarah is the manager here, and both Bob and Charlie report directly to her. There are no additional levels of hierarchy beneath Sarah. Some constraints to keep in mind include the maximum number of rows in the employee table, which is capped at 10,000. Additionally, the company hierarchy is guaranteed to be a valid tree, meaning there are no cycles. This ensures that the reporting structure is well defined. Finally, edge cases to consider include scenarios where a manager has no reports at all, which would lead to an empty output table, or situations where the hierarchy is very deep or wide, which the solution must handle efficiently. To tackle the problem of identifying all employees who report directly or indirectly to a given manager, we need to think about hierarchical relationships, which can be represented as either a tree or graph structure. The first approach we considered was the brute force method. The idea here is simple. For each employee, we recursively trace their manager ID to see if it eventually leads to the given manager. While this method is straightforward to implement, it's highly inefficient because we end up traversing the hierarchy repeatedly for each employee. This leads to a time complexity of n squared, which makes it impractical for large datasets. Recognizing this inefficiency, we explored a more optimized approach using an adjacency list combined with depth-first search, or DFS. By creating an adjacency list, we represent the hierarchy as a directed graph where each manager points to their direct reports. Then, we use DFS to traverse the graph starting from the given manager, collecting all reachable nodes. Constructing the adjacency list takes n, and the DFS traversal also takes n, resulting in an overall time complexity of n. This approach avoids redundant computations, making it far more efficient than brute force. The optimized approach with an adjacency list and DFS offers several advantages. It's efficient, with a time complexity of n, and avoids redundant computations by pre-computing the hierarchical relationships. The space complexity is also n, which accounts for the adjacency list and the recursion stack during DFS. Another option we considered was implementing the solution using SQL, specifically with recursive common table expressions, or CTEs. In this approach, we define a base case to find employees who directly report to the given manager, and then recursively find employees who report to them. This method is efficient for relational databases, as it leverages database optimizations for handling hierarchical data. However, it has a significant drawback: it requires SQL-specific knowledge and cannot be easily translated to most programming languages. After evaluating these options, we chose the adjacency list approach with DFS as our primary solution. Its simplicity, efficiency, and broad applicability across programming languages make it the most practical choice. Additionally, we observed that this problem fundamentally involves traversing a graph-like structure, and using an adjacency list minimizes redundant computations while making the traversal process straightforward. The adjacency list approach with DFS was ultimately chosen because it strikes the ideal balance between efficiency, simplicity, and versatility. With a time complexity of O(n), it's well suited for large datasets, and by pre-computing the hierarchical relationships, it avoids the inefficiencies of the brute force method. The implementation is intuitive, making it accessible to a wide range of developers. When comparing the trade-offs, the brute force approach, while simple, is computationally prohibitive for larger inputs. The SQL/CTE method, on the other hand, is efficient within database environments but lacks cross-platform portability. The adjacency list approach avoids these limitations, offering a solution that is both elegant and practical for general-purpose programming. In conclusion, this method ensures optimal performance while maintaining implementation simplicity, making it the best choice for solving the problem comprehensively and efficiently. In this problem, we need to identify all employees who report directly or indirectly to a given manager. Think of the organizational structure as a tree, where each node represents an employee, and the edges define the reporting relationships. The input consists of a list of employee-manager pairs, along with the ID of the manager whose hierarchy we need to explore. Our goal is to return a list containing all employees under this manager. To solve this, we'll use a depth-first search, or DFS, which is a method of exploring hierarchical or graph-like structures systematically. First, we'll construct a tree representation using an adjacency list. This list will map each manager to their direct reports. For instance, with the input relationships 2, 1, 3, 1, 4, 2, and the manager ID 1, the adjacency list would look like this: 1, 2, 3, 2, 4, 3, 4. This structure allows us to efficiently retrieve the direct reports for any manager, forming the foundation for our traversal algorithm. Once we have the adjacency list, we'll prepare to store the results. An empty list, result, will be used to keep track of employees who report to the given manager, whether directly or indirectly. The next step is to define a recursive DFS function, which will traverse the reporting hierarchy. This function, DFS manager, will retrieve the list of direct reports for the current manager from the adjacency list. For each direct report, we'll add that employee to the result list and then call DFS recursively for that employee. This ensures that we not only capture direct reports but also explore all indirect reports further down the hierarchy. Finally, we'll initiate DFS by calling DFS manager with the given manager ID. This will populate the result list with all employees in that manager's hierarchy. Once the traversal is complete, we return the result list as the output. This approach ensures that all levels of the reporting structure are explored systematically. The adjacency list is central to the algorithm, as it provides an efficient way to represent the relationships in a sparse graph. This structure is compact and allows for quick retrieval of direct reports for any manager. In terms of performance, the algorithm is scalable, with a time complexity of O(n plus E), where n is the number of employees and E is the number of reporting relationships. This makes it suitable for large datasets. Additionally, it's important to handle edge cases. For example, if the given manager has no direct or indirect reports, the output should be an empty list. Cyclic relationships, though invalid in a typical hierarchy, can be checked to avoid infinite recursion. We'll use two main data structures here, the adjacency list to store the relationships and a result list to collect the IDs of all employees under the given manager. To illustrate, consider the input relationships 2, 1, 3, 1, 4, 2, 5, 2, and manager ID 1. We'll walk through an example next to see how the algorithm works step by step. Let's execute the algorithm with the given example. First, we'll build the adjacency list from the input. The resulting structure is 1, 2, 3, 2, 4, 5, 3, 4, 5. This organizes the hierarchy in a way that's easy to traverse. Next, we initialize the result list, starting with an empty array result equals. Now, we begin the DFS traversal by calling DFS1. Starting with Manager 1, we add their direct reports 2 and 3 to the result list. For Employee 2, we recursively call DFS, adding their reports 4 and 5 to the result. Both 4 and 5 have no reports, so the recursion stops there. Returning to Employee 3, we find they also have no reports, so the recursion concludes. At the end of this process, the result list contains 2, 3, 4, 5, which represents all employees reporting to Manager 1, either directly or indirectly. Analyzing the algorithm, the time complexity is O, n plus E, where n represents the number of employees and E represents the number of relationships in the input. This is because we traverse each employee and their relationships exactly once. The space complexity is also O, n plus E, accounting for the adjacency list and the recursion stack. Let's look at the implementation. We start by building the adjacency list using a dictionary where the keys are manager IDs and the values are lists of their direct reports. Then, we initialize an empty result list. We define the DFS function, which iterates through the direct reports of a manager, adds them to the result list, and recursively processes their reports. Finally, we invoke the DFS function starting with the given manager and return the populated result list. This efficient and straightforward implementation captures the entire hierarchy under the specified manager. Here's an example to see the code in action. If we input the relationships 2, 1, 3, 1, 4, 2, 5, 2, and specify manager 1, we call the function findEmployees. The algorithm builds the adjacency list, initializes the result list, and performs the DFS traversal. The output is 2, 3, 4, 5, which confirms that employees 2, 3, 4, and 5 all report to Manager 1, either directly or through others in the hierarchy. This example demonstrates how the algorithm works step by step, producing the correct result by systematically exploring the reporting structure. With its efficiency and clarity, this approach is well suited for solving the problem on both small and large scales. This implementation solves the problem of finding all employees who directly or indirectly report to a given manager. The code begins by importing defaultDict from the Collections module, which helps in creating a dictionary to store the manager-employee relationships efficiently. The findEmployees method is the main function. It takes two inputs, manager, the ID of the manager whose reporting hierarchy we need to determine, and employee_manager_pairs, a list of tuples where each tuple represents an employee and their direct manager. In step 1, we build an adjacency list hierarchy using defaultDict list. This adjacency list maps each manager to a list of direct reports. We iterate over the employee_manager_pairs and populate the hierarchy. For example, if employee 2 reports to manager 1, the hierarchy will map 1 to a list containing 2. In step 2, we define a helper function DFS that uses depth-first search to traverse the hierarchy tree. The DFS starts from the given manager and recursively visits all employees in the hierarchy, adding them to the result list. For each employee directly reporting to the current manager, we append the employee to the result and recursively call DFS for that employee to explore their subordinates. Finally, we initialize an empty list result, called DFS starting from the given manager, and return the result list, which contains all employees who report directly or indirectly to the manager. This approach ensures that the hierarchy is traversed efficiently, and all employees are collected in O(n) time, where n is the total number of employee-manager relationships. The use of DFS ensures that all levels of the hierarchy are explored completely. Here, we begin by defining the findEmployees method, which takes a manager ID and a 2D array of employee-manager pairs. The goal is to identify all employees who report directly or indirectly to the specified manager. First, we construct an adjacency list to represent the hierarchy. This is achieved using a hash map where each manager is a key, and the corresponding value is a list of employees reporting to that manager. we loop through the employee-manager pairs array, extracting each employee and their respective boss. Using the putIfAbsent method, we initialize the list for a manager if it doesn't already exist, and then we add the employee to this list. Next, we prepare to traverse this hierarchy using depth-first search, DFS, to gather all employees under the given manager. We initialize a result list to store the output and call the DFS helper method, passing the manager ID, the hierarchy map, and the result list. The DFS method will recursively explore the hierarchy, starting from the given manager, and populate the result list with all employees who directly or indirectly report to them. The DFS method is implemented to recursively traverse the hierarchy. It begins by checking if the current manager exists in the hierarchy map. If not, this means the manager has no direct reports, so we simply return. Otherwise, we iterate through the list of employees who report to the current manager. Each employee is added to the result list, and we make a recursive call to DFS for that employee. This ensures that we explore all levels of the hierarchy beneath the given manager. By the time the recursion completes, the result list will contain all employees who report, either directly or indirectly, to the specified manager. This recursive approach effectively handles the tree-like structure of the hierarchy. Here we have a simple hierarchy example where the given manager is 2, and the employee-manager pairs are 1, 2, 3, 2, and 4, 1. The first step involves building the hierarchy as an adjacency list. We start with an empty default called hierarchy and process each pair one by one. First, we add employee 1 under manager 2, resulting in a hierarchy of 2, 1. Then, we add employee 3 under manager 2, updating the hierarchy to 2, 1, 3. Finally, we add employee 4 under manager 1, resulting in the complete hierarchy 2, 1, 3, 1, 4. Next, we perform a depth-first search, or DFS, starting from manager 2. The DFS function begins with manager 2 and an empty result list. Since manager 2 has employees 1 and 3, we start by appending 1 to the result and recursively call DFS for manager 1. At this point, the result becomes 1, and we proceed to explore the employees under manager 1, which is employee 4. Continuing the DFS from manager 1, we append 4 to the result, making it 1, 4, and then recursively call DFS for employee 4. Since employee 4 has no direct reports, the function returns, and we go back to manager 2's DFS. Now, we append 3 to the result, updating it to 1, 4, 3, and call DFS for employee 3. Again, since there are no employees under manager 3, the function returns. At this point, the DFS traversal is complete, and the final result is 1, 4, 3. This represents all the employees who ultimately report to manager 2, in the order they were visited during the DFS traversal. Now let's look at a more complex example with multiple sub-managers. The given manager is 1, and the employee-manager pairs are 2, 1, 3, 1, 4, 2, 5, 2, and 6, 3. As before, we start by building the hierarchy. Employee 2 is added under manager 1, creating a hierarchy of 1, 2. Then, employee 3 is added under manager 1, updating the hierarchy to 1, 2, 3. Next, employee 4 is added under manager 2, resulting in 1, 2, 3, 2, 4. Similarly, employee 5 is added under manager 2, giving 1, 2, 3, 2, 4, 5. Finally, employee 6 is added under manager 3, completing the hierarchy as 1, 2, 3, 2, 4, 5, 3, 6. Once the hierarchy is built, we perform DFS starting from manager 1. The DFS begins with an empty result list. Manager 1 has employees 2 and 3, so we first append 2 to the result, making it 2, and recursively call DFS for manager 2. Manager 2 has employees 4 and 5, so we proceed to explore them. In manager 2's DFS, we append 4 to the result, making it 2, 4, and call DFS for employee 4. Since employee 4 has no direct reports, the function returns. Next, we append 5 to the result, updating it to 2, 4, 5, and call DFS for employee 5. Again, since employee 5 has no reports, the function returns. At this point, we return to manager 1's DFS and append 3 to the result, making it 2, 4, 5, 3. We then call DFS for manager 3, who has 1 employee, 6. In manager 3's DFS, we append 6 to the result, resulting in 2, 4, 5, 3, 6, and call DFS for employee 6. Since employee 6 has no direct reports, the function returns. Finally, the DFS traversal is complete, and the result, 2, 4, 5, 3, 6, represents all employees reporting to manager 1 in the order of their visitation. In this example, we consider the scenario where the given manager has no employees. The manager is 5, and the employee-manager pairs are 1, 2, 2, 3, and 3, 4. We start by building the hierarchy. Employee 1 is added under manager 2, creating 2, 1. Then, employee 2 is added under manager 3, resulting in 2, 1, 3, 2. Finally, employee 3 is added under manager 4, completing the hierarchy as 2, 1, 3, 2, 4, 3. Now, we perform DFS starting from manager 5. Since manager 5 has no employees in the hierarchy, the DFS function immediately returns an empty result. The final output is an empty list, indicating that there are no employees who report to manager 5. When analyzing the time complexity of this solution, we need to consider 2 main steps. First, we build the adjacency list to represent the reporting hierarchy. This involves iterating through the employee_manager_pairs list, which contains n pairs, and for each pair, we append the employee to their manager's list in the dictionary. Since appending to a list is an O(1) operation on average, constructing the entire adjacency list takes O(n) time. Next, we perform a depth-first search, DFS, to gather all employees who report, either directly or indirectly, to the given manager. In the worst-case scenario, the hierarchy forms a tree-like structure where all employees are connected in a single chain of reporting. Here, the DFS visits each employee exactly once, processing their direct reports. Since there are n employees in total, this traversal also takes O(n) time. Combining these 2 steps, the overall time complexity of the solution is O(n). Now let's look at the space complexity. The first factor is the adjacency list, which represents the hierarchy. This is stored as a dictionary where each key corresponds to a manager, and the value is a list of employees who report to that manager. In the worst-case scenario, where every employee has a unique manager, the dictionary will have O(n) keys, and the total size of all the lists will also sum to O(n). Thus, the space required for the adjacency list is O(n). The next factor is the call stack used during the DFS traversal. In the worst case, if the reporting structure is a single chain, the recursion depth will be O(n), as every employee is visited in sequence. On the other hand, in the best-case scenario where the hierarchy is flat, the recursion depth is O(1). Another component of the space complexity is the result list, which stores all employees who report to the given manager, either directly or indirectly. In the worst-case scenario, where all n employees are part of the hierarchy under the given manager, this list will contain all n employees. Therefore, the space required for the result list is O(n). Combining the space used for the adjacency list, O(n), the call stack for DFS, O(n) in the worst case, and the result list, O(n), the total space complexity of this solution is O(n). We can further analyze the solution by breaking it into best, average, and worst-case scenarios. In the best case, if the hierarchy is flat and the given manager directly manages all employees, the DFS only recurs once for each employee, resulting in minimal recursion depth of O(1). The time complexity remains O(n), and the space complexity is also O(n). In the average case, where the hierarchy is a mix of deep and flat structures, the recursion depth and traversal costs are intermediate, but the time and space complexities remain O(n). In the worst case, where the hierarchy forms a single chain of employees, the recursion depth reaches O(n), but even here, the time and space complexities are still O(n). This consistency across all scenarios demonstrates the efficiency of our approach. Finally, let's compare this approach to a naive solution. A simple but inefficient method would involve repeatedly iterating through the employee_manager_pairs list to find all employees reporting to the given manager. This would require multiple scans of the list, leading to a time complexity of O(n)² in the worst case. In contrast, our current approach uses an adjacency list in DFS, which reduces the time complexity to O(n) by processing each employee only once. The space complexity is also optimized, as we only store the hierarchy and the result list, both of which grow linearly with the number of employees. To summarize, building the adjacency list takes O(n) time, and the DFS traversal also takes O(n), giving an overall time complexity of O(n). The space complexity includes the adjacency list, DFS call stack, and result list, all of which contribute O(n), leading to an overall space complexity of O(n). When solving this problem, there are several common mistakes to watch out for. First, many people confuse direct and indirect reports. It's important to remember that we're not just looking at the employees who report directly to the manager but also those who report indirectly through other employees. This requires a complete traversal of the hierarchy, ensuring every level is accounted for. Another common pitfall is inefficient traversal. If you rely on a brute force approach, such as repeatedly iterating over the dataset with nested loops, the time complexity can quickly reach O(n squared, or worse. To avoid this, structure your solution as a graph traversal, using either DFS or BFS combined with a hash map for quick lookups. Additionally, input parsing errors can cause issues, especially if you assume there are no cycles or fail to validate the input for anomalies like missing managers. Always check for edge cases like empty datasets, managers with no subordinates, or even cycles within the hierarchy. Lastly, when using recursion, ensure the base case is properly defined to prevent infinite loops or stack overflow, especially for large or deeply nested trees. Now, let's consider some insights that are particularly useful in interview scenarios. This problem can be viewed as a graph or tree traversal challenge. You should be prepared to explain the differences and trade-offs between DFS and BFS. While both have O(n) time complexity, their space requirements differ. DFS uses a stack, which could be the function call stack if implemented recursively, while BFS uses a queue. To make traversal efficient, you can use a hash map to map each manager to their direct reports. This structure allows for constant time lookups during traversal. Another key point is to proactively address edge cases during the interview. Discuss scenarios like cycles in the hierarchy, missing nodes, or isolated employees. Finally, scalability is an important consideration. For instance, if the dataset includes 10,000 employees or more, how does your solution handle that scale in terms of time and space? Being able to articulate these points will show your interviewer that you understand both the problem and its practical implications. This problem also shares similarities with several related problems on LeetCode, which can help deepen your understanding. For example, LeetCode 133, Clone Graph, involves traversing and replicating a graph structure, which is similar to navigating a hierarchy. LeetCode 207, Course Schedule, focuses on cycle detection in a directed graph, a concept that's crucial for validating the input hierarchy in this problem. Another relevant problem is LeetCode 1506, Find Root of N-ary Tree, which requires identifying the root node in a tree structure, a foundational step in many hierarchy-based problems. Lastly, LeetCode 310, Minimum Height Trees, emphasizes efficient analysis of tree properties, which shares conceptual overlap with understanding and traversing hierarchical data. Exploring these problems can give you a broader perspective and help you recognize patterns across different scenarios. There are also alternative approaches you can consider for solving this problem, each with its own trade-offs. Using DFS recursively is a straightforward method for hierarchy traversal. It's concise and easy to implement, but it can lead to stack overflow for very deep trees unless tail call optimization is available. Alternatively, you could opt for BFS, which uses a queue to process one level of the hierarchy at a time. This iterative method avoids recursion depth issues and provides controlled memory usage, but it's slightly more complex to implement. Finally, if the hierarchy is represented as a directed acyclic graph, you might consider topological sorting to determine all nodes influenced by a given manager. While this approach is useful for managing complex dependencies, it may be overkill for simpler tree structures. Choosing the right method depends on the problem constraints and the specific requirements of the dataset you're working with. Great job! To wrap up, we summarized the key points of this problem, including the algorithm used, its applications, and important takeaways. Keep practicing similar problems to reinforce your understanding. Thank you for watching, and don't forget to like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!